Okay, there's a concept now in physics called position graphs and velocity graphs. And I'm telling you now that it takes a little bit and a little thinking and a little creativity and imagination to see all this, and it's really important. So I suggest if you are a little confused after watching these videos, go on YouTube and look at what other people have to say. There's a lot of good explanations out there, and if mine doesn't work, I would recommend you find someone who can explain it maybe in a little different way that will help you understand. But we are going to be talking about motion now, and it's not as simple as Aristotle thought. Aristotle was a genius. He was amazing, but it has to do it's a little more complicated. So we're going to just start talking about what velocity is. So we have this picture. Imagine that is a poorly drawn car. And this poorly drawn car is moving forward on a road in this direction. Now if I put dots here, each one of those dots symbolizes the same amount of time. And so the distance between each dot is about the same. That means this car must be moving at a constant rate. So an xt graph is position over time. This is always our time down here, and then this is x, our position. And so we're just keeping track, where are we over time? And so what might happen here is that our car started a certain amount forward, say if I drew a little graph here, the car kind of started over here. So at time equals 0, my car is forward a little bit. At time equal 1, it has moved forward a certain amount, and so we want it to be further up on the position. And at time equal 2, we want to be even further up. But they're all moving at the same rates. So what we have here, if we mapped out the position, is a car over time is getting further and further away. That is the xt graph, or the position graph. There's another graph to analyze this situation called the vt graph, which is velocity versus time. It has nothing to do with where the car is. It's asking the question, how fast is the car at those times? Okay, now this graph is a lot simpler. At the very beginning, this car is going at a certain speed. Let's just call it that. Let's just call it like, I don't know, like 5 meters per second. And it looks like, based on these dots here, it is not increasing or decreasing its rate. So at every second, if we checked the time, it would always be moving at the same speed. So this is keeping track of the velocity. It is moving forward, which is why it's a positive 5, and it is constant. It is not changing at all. So I said speed earlier, and I want to make this very clear. Velocity is not speed. Okay? Now, in a car, you can talk about speed because when you look at the speedometer, it will always give you a number 0 or above, even when you're in reverse. Now, velocity, it matters if you're going backwards. In velocity, if I was going -2 meters per second, that means I'm going backwards 2 meters per second. Speed doesn't care which direction you're going. It's just going to tell you how fast are you going at that time. Okay, so we're going to actually talk about average velocity with some numbers here. We get some formulas. Average velocity is change in position over change in time. So I'll write that out here. Another way to write it is displacement over change in time. So that's what that little delta here means. That means change. Now, here, for example, if I went uh, from 5 miles away to 7 miles away from a certain city, sorry, 75, the actual displacement, the change in the position, would be 70. And if it took me 2 hours, well then the change in time is going to be 2. So my velocity, my average velocity, is going to be 70 over 2. So we subtract the positions I was in, and then we divide by the number of hours it took. Okay? So, for example, let's say that I travel 2 hours and go 40 miles. I spend another 2 hours and travel 40 miles back. Now, what's the velocity here? Now, this is going to seem kind of weird, but velocity is the total displacement. If I look at where I begin and where I end, how different are they? So in my example above here, if I went from 5 miles away to 75 miles away, the difference there is actually 70. But in here, if I go 40 miles and return 40 miles, the actual change in x is going to be 0. Now, the actual change in time is 4. If I take anything and divide 0 and divide it by anything, I'm going to get 0 miles per hour. So we have to take into account that this is an average, meaning over the entire trip, what was the total velocity, total change divided by the total time. So it can lead to some interesting things. Now I'm going to draw, as another example, a graph here of someone traveling. Now this is going to be time, this is going to be position. Okay? And I'm going to draw a dotted line here to show that they did actually end up a little higher than before. Now, if I was to include a couple more dots here, I'll label them A, B, C, and D. Now, we're going to imagine a couple different time frames here. If I went from A to B along the red curve here, you would think about this as the change in x, and then also you would think about this as your change in t. Okay? So when you find change in x over change in t, you're finding the slope of this line that I'm drawing here. Slope is your velocity. And so, in that case, we would have a positive slope. For example, if this was 4 and this was 2, it'd be 4 over 2, which is 2. The speed would be 2 meters per second, possibly. So let's change the color here. Let's say that I started at A and then looked at the point C here. Now my velocity is changing all the time, but if I'm looking at the average velocity over those 2 points in time, I would care about the total change in x and the total change in time there. Now in this case, total change in x is going to be negative. Maybe that's going to be negative 4, because I went, and even though I went forward 4 and then went back 4 to negative 4, I would have traveled 4 up and then 8 back to get here. And let's say the total time is, I don't know, 4. If I figure out the slope for the blue part, it's going to be negative 4 over 4, which is negative 1. So on average, I've traveled negative 1 meters per second. Okay, now for the last one here. It's getting a little messy here. If I travel from here to there, from A to D, Now, because it is above, I'm going to have a positive speed. I have ended up going forward a little bit, but it's going to be smaller than my original a to b, because going from a to b, you're moving forward a lot more. So, there's this concept here where I'm taking averages here. I'm not looking at everything that goes on in between. I'm just taking 2 points and looking at the change in the x and the change in the y. So, before we move on, there is one last concept called instantaneous velocity. Okay, so if we had a graph of our movement here, now at this point right here, if I chose another point here and found the slope there, that would kind of tell me the speed there. It's pretty close. If I got a point closer, that would tell me the speed there with that slope. It's pretty close, the velocity. As my points get closer and closer and closer to this point right here, I'm going to get a line that is more and more accurate to the actual speed of the object right there. So the same thing like back here. If I choose a point back here and do a slope here, it is not a perfect velocity there, but it's about an average and it's pretty close. And as my points get closer and closer, if I find smaller and smaller time differences, we're going to find something called the instantaneous slope, the perfect slope right there, which is our velocity. And so just to keep this in mind, when we're doing this, we're kind of estimating speeds. But there is an instantaneous velocity. How fast are you actually going? That you can kind of find using these slopes. You just have to get points that are really close together.